Hi everyone, it's Mrs. Jennison here, and today's lesson we will be looking at the Haber process. This lesson is for triple science students only. Remember, as with all of our lessons, it will be really useful if you had a pen and a piece of paper so that you could work through the activities with us as we go through the video. Our challenge today is to be able to explain what is meant by the term equilibrium and state factors which will affect reversible reactions. Our aspire is to be able to explain and evaluate the effects of changing the conditions of temperature and pressure on the Haber process. So let's flip back to another lesson and have a little bit of a recap before we get into the Haber process. In a chemical reaction, what does the following symbol mean? And what effect does that have on the yield of a reaction? So the symbol means that the reaction is reversible, which means it can go both ways. That means that the products can reform the reactants, which is why reversible reactions typically have a low yield. Now I'm going to play a little video. It is a song that goes through some of the things that can affect the position and the shifting of an equilibrium. It's a personal favourite, so I hope you enjoy it.
To and fro, forwards and back, simultaneous it flows. Reactants becoming products at the same rate reverse goes. It goes forever, system closed. Nothing gets in or out. But once the system's open, you might hear this shout. Stress, shift, changing concentration. Stress, shift, changing concentration. The capital yes is so much fun. Equilibrium shift for everyone. If you add reactant, collisions more between. It shifts towards the product side. Product increases seen. If you add a product, collisions will improve. The shift is toward the reactant side, and products are removed. If the concentration goes down, whichever one you choose, then the shift's the other way, towards whatever you remove. Stress, shift, changing concentration. Stress, shift, changing concentration. The shot to yes is so much fun. Equilibrium shift for everyone. If you raise the temperature, shift endothermically, move away from the side with heat, and you will surely see. If you cool the system down. It's an exothermic shift. Select towards the side with heat. The temperature will lift. If you raise the pressure, the side with less gas will score. If instead you lower P, shift to the side with more. Stress, shift, changing concentration. Stress, shift, changing concentration. The chateliers is so much fun. Equilibrium shift for everyone. Stress, shift, changing concentration. Stress, shift, changing concentration. The chateliers is so much fun. Equilibrium shift for everyone.
So, as we heard in the song, reversible reactions go backwards and forwards, and they largely occur in the same conditions at the same rate. If the forward and the backward reaction are occurring at the same rate, that is said to be in dynamic equilibrium, which means there is no overall change in the amount of products and reactants, even though the reactions are ongoing. So as you can see in the little diagram at the side, the reactants are forming products, and then the products are reforming those reactants. And at any one time, if you looked at that reaction, you'd have the same amount of reactants and products. Now, dynamic equilibrium can only take place in a closed system. Otherwise, the products would escape and then they couldn't reform the reactants. The position of dynamic equilibrium is not always at a halfway point. It may be at a position where there are mainly reactants with little product, or vice versa. The position of the equilibrium is influenced by three main factors: the temperature, the concentration, and if we are looking at a reaction involving gases, the pressure. You can add a catalyst to a reversible reaction, and it will speed up the time it takes for it to reach equilibrium, but it will not change the position of the equilibrium because it will actually speed up the forward and the reverse reaction. So I'm going to insert a little video that goes through some really key facts on the Haber process. After that video, I'm going to ask you a few questions.
You have likely produced ammonia in the laboratory from the thermal decomposition of ammonium chloride or from the reaction of ammonium and hydroxide ions. Have you ever wondered how ammonia is produced on an industrial scale? In this lesson, we will learn about the Haber process to produce ammonia, developed during World War I by Fritz Haber and Carl Bosch. For their efforts and contributions to developing large-scale industrial processes, they were awarded with Nobel Prizes in chemistry. The Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Hydrogen is obtained from the reaction of methane and steam, producing carbon monoxide as a byproduct. The hydrogen produced from this reaction also reacts with oxygen from air, producing water and leaving nitrogen behind. Recall that air is 77% nitrogen. These gases are then compressed and delivered to the reactor, where ammonia is produced. These gases are then cooled down and ammonia is liquefied, ready to be tapped off. Unused hydrogen and nitrogen are recycled back to the reactor. Let's revisit this reaction again. Note that this is a reversible reaction and that the forward reaction is exothermic. The Haber process uses Le Chatelier's principle to maximize ammonia production while keeping operating and production costs in mind. Le Chatelier's principle tells us that increasing pressure will favor the side with fewer moles. for our case, the production of ammonia. It would make sense to conduct the reaction at a very high pressure, but we must also remember that it is expensive to build and operate a plant that can withstand such high pressures. Therefore, a compromise pressure of 200 atmospheres is used. Let's keep Le Chatelier's principle in mind. What do you think is the best temperature conditions to maximize ammonia production? Please pause the video to think about this and resume once you are ready. Since the forward reaction is exothermic, it would make sense to conduct this reaction at a low temperature. The compromise temperature is 400 to 450 degrees Celsius, which is not exactly low, but not too high. If a low temperature were used, the rate of reaction would be very slow, though the exothermic reaction would be favored. It would actually take a long time for equilibrium to be reached, so a compromise temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yield. The yield of this process is 10 to 20%. Remember from the introduction that unused gases are recycled, so no reactants are wasted. As well, an iron catalyst is used in this process. The presence of the catalyst does not affect the position of equilibrium, but increases the rate at which equilibrium is reached. In conclusion, the Haber process is the industrial process to produce ammonia from hydrogen and nitrogen. It is conducted at 400 to 450 degrees Celsius and at 200 atmospheres in the presence of an iron catalyst. These are compromise conditions in order to maximize ammonia production and economic profit.
Following on from the video, could you please answer the 5 questions on the screen? What are the raw materials for the Haber process? Where do they come from? What happens to the unreacted reactants? How is the ammonia separated from the reactants? And what is the catalyst that is used? Okay, so what are the raw materials? They are nitrogen and hydrogen, and nitrogen comes from the air and the hydrogen comes from methane. The unreacted reactants are recycled back into the reactor, and the ammonia is separated by cooling the mixture, and the ammonia condenses whilst the rest of the reactants remain a gas. The catalyst is iron. So why is ammonia so useful? Well, first of all, it's an important compound in the manufacture of fertiliser and other chemicals such as cleaning fluids and floor waxes. It is made industrially by reacting nitrogen and hydrogen in the Haber process, which is a reversible reaction, so it never goes to completion. So you can see the equation on the screen at the moment. So we've got nitrogen reacts with hydrogen and forms ammonia. Now, why could ammonia being produced by this reaction cause a problem for us in industry? It's because the reversible reactions have a low yield, as we mentioned at the start of the lesson, and low yields are not beneficial to us in industry because that means that we are wasting some reactants essentially. So industrial processes are normally manipulated to maximise that yield, and that's the main thing that we're going to look at for the rest of this lesson. So I've got a graph on the screen, and what I'd like you to do is I'd like you to use that graph to tell me what the best conditions for producing ammonia would be. Then I want you to think about why those conditions may be an issue. And there's a little hint on the screen. Think about rates of reaction. So, from the graph, the highest yield of ammonia would theoretically be produced by using a low temperature, and the specific temperature here would be 350 degrees C, and a high pressure. Now the issues there would be in the fact that the low temperature would actually lead to a lower rate of reaction. And that means it would take significantly longer for the ammonia to be produced. So what you'd gain in terms of yield would be counteracted by how long it takes to produce that ammonia. Also, a high pressure means that you are using stronger, more expensive equipment, which significantly increases the cost of production, which wouldn't be beneficial in terms of industry. So, what we can do is we can use our knowledge of reversible reactions and conditions to explain why those conditions would be beneficial and then manipulate the reaction. So, you may remember from a previous lesson that the position of an equilibrium will shift to cancel out any change in conditions. That means that by changing the conditions in the reaction, it can be shifted from one direction to the other. So if you increase the pressure, the equilibrium will shift to the side with the least particles. If you can increase the concentration of the reactants, the equilibrium will shift to create more products. If the forward reaction is exothermic and you increase the temperature, the equilibrium will shift to the endothermic route. So I'm going to insert now a couple of videos that are just me modelling how manipulating those conditions will affect the Haber process. As you can see on the screen, I've written the equation for the reaction that produces ammonia. Now remember that this is a reversible reaction. You learned in a previous unit about reversible reactions and how the position of their equilibrium can shift due to a principle called Le Chatelier's principle. Now, what I'm going to go through in this first video is how changing the temperature can shift the position of this equilibrium. So as you can see from the arrow, the forward reaction is the exothermic reaction. That means that this forward reaction will release energy as heat, whereas the reverse reaction will take in energy as heat. So, what would happen if I increased the temperature? Okay, so the first thing that will happen is if I increase the temperature, the reaction will shift in the endothermic route, which in this case would be to the left, because it's going to take in that thermal energy. That will reduce the yield of NH3, of ammonia, and produce more nitrogen and hydrogen. Now that's one of the reasons why this reaction actually favours a lower temperature. So let's go through what would happen if I decreased the temperature. If that happens, this reaction will shift in the exothermic route, which is to the right in this case, which means it would increase the yield of ammonia. That 3 looked like a 2 then, sorry. And it would reduce the amount of nitrogen and hydrogen. So now let's have a look at how pressure can affect the position of this equilibrium. Now, the thing that we need to look at when we are talking about pressure is the number of moles or molecules on each side of the reaction. So what I'm going to do, and what I always do, is I put a little dot above to represent the molecules on that side. So here, I would have 1 nitrogen and 3 hydrogen molecules. So on that side, I've got 4 molecules. And on this side, I've got 2 molecules, 2 ammonia molecules. Now, a lower pressure would be a side with less molecules on. So if we are thinking about counteracting the changes here in this reversible reaction, if we put this under stress by increasing the pressure, it will shift to the side with less molecules to counteract that change. So let's have a look at how increasing the pressure will affect this reversible reaction. If I increase the pressure, it'll shift to the side with less molecules. Which on this case is to the right. That means we're going to get a higher yield or an increased production of ammonia and decreased nitrogen and hydrogen. So what would happen if I decrease the pressure? If I decrease the pressure, it'll shift to the side with more molecules, which in this case would be to the left. This would give us increased production of nitrogen and hydrogen and a decreased production or yield of ammonia. So essentially, we end up using a compromise when we are getting our conditions for this reaction. We want a high yield, but we also want a fast rate of reaction. So we have to compromise conditions to make sure that we get both. That means that the Haber process is carried out at 450 degrees Celsius and 200 atmospheres of pressure. Now, quick exam tip. Make sure if you are asked for these that you also quote the units, because they do expect that, especially if they're not given on the line. The most important factor in deciding these conditions is not just the yield, it is the total cost. And there are other costs involved in this process. So we also have the cost of the raw materials to consider, equipment, energy, and the cost of the workers. So what else can be done to maximise productivity and minimise cost? Well, they use an ion catalyst. Even though that speeds up the forward and the backward reaction, it doesn't affect the position of the equilibrium, but it does increase the rate of the overall reaction. The ammonia is cooled and liquefied and removed as it is produced, which means this is a continuous process. As you are removing a product, you are decreasing the concentration of the product so that the equilibrium will shift to form more. We also reuse any unreacted nitrogen and hydrogen, which minimises the cost of the raw materials, and it gives us those molecules another chance to react. So we're going to start looking at some exam questions on this now. So the diagram shows how nitrogen is used in the Haber process to produce ammonia. So we've got nitrogen going in with gas X into the reactor. We've got a condenser, ammonia, and then unreacted gases going back in. They'd like you to name gas X that is obtained from methane, give the approximate temperature and pressure used in the reactor. The mixture of gases from the reactor cools in the condenser, and they want you to suggest why ammonia condenses but the other gases do not. If you need more time on any of these questions today, just pause the video so that you've got sufficient time to answer them. So the next question. The graph in figure 1 shows a flow diagram for the Haber process. So we've got nitrogen and hydrogen going into the reactor containing iron and forming a mixture of gases. Hydrogen is a gas obtained from methane. Name one source of methane. Air is the source used to produce nitrogen for the Haber process. Suggest why air must not get into the reactor. And then describe what happens to the mixture of gases from the reactor. So the next question. The graph in figure 2, which is to the right, shows the percentage yield of ammonia using different conditions. The first thing they want you to do is to use figure 2 to suggest the conditions that produce the greatest yield of ammonia. Then they'd like you to use figure 2 to suggest and explain why the conditions used to produce ammonia in the Haber process are a temperature of 450 degrees C and a pressure of 200 atmospheres. Now, you may need to pause to give yourself a little bit more time for the second part of that question. Remember that when you are being asked to explain why, you have to give the reason for something happening. So you need to be saying why we compromise with those conditions. Okay, so I've put the mark scheme on the screen even. The first part was hydrogen. That's what we make from methane. The conditions were 450 degrees C and 200 atmospheres. If you only put 450 and 200, you could have 1 mark. You had to have the units for the second mark. Ammonia has a higher boiling point than the other gases, or you could say that the other gases have lower boiling points. Then the source of methane is natural gas. Air can't get into the reactor because air contains oxygen that would react with the hydrogen gas. You could have also said it would have reacted with the catalyst. Now, the mixture of gases is cooled, the ammonia condenses or liquefies, and the nitrogen and hydrogen are returned into the reactor because they are remaining as gases. From the graph, the conditions were 200 degrees C and 1000 atmospheres. Then when we were talking about the compromise of 450 and 200 atmospheres, we had to talk about the fact that the reaction was reversible. And the forward reaction is exothermic, so an increased temperature lowers the yield, but it would also decrease the rate of reaction. Now that phrasing would have given you 2 marks. Then talking about the pressure, a higher pressure would increase the yield, but it would also increase the costs or the energy needed for that reaction to take place. So that's everything for this video, and I will see you soon. Bye!